Hi, I'm Jasper. In this talk, I'll be discussing a joint work with Paul Valiant on the fundamental problem of mean estimation. Let me start with the concrete problem statement. Suppose we're given n independent samples drawn from some unknown distribution d over the real numbers. The problem is to estimate the mean of the distribution to within additive error epsilon, failing with probability most delta. And the goal is to minimize the sample complexity of our mean estimator mu hat, namely the number of samples n required to satisfy this epsilon delta guarantee. Now, this mean estimation problem is obviously very fundamental in statistics, but it is also highly relevant in algorithm design as well. As an example, suppose we're given some combinatorial object, let's say a graph or maybe some stream, and there's some parameter of it that we're trying to estimate. A common approach is to design and compute some distribution whose mean or expectation is exactly the parameter we're trying to estimate. And therefore, mean estimation as a problem is also very important in computer science. Now you might be thinking, don't we already know how to do mean estimation? Like, why can't we just take the sample mean, namely just take the average of all the samples we've seen and return that as the estimate? The issue is that the sample mean is actually very suboptimal in sample complexity, even in this one-dimensional case. So of course, there are things that the sample mean is good for, and in fact optimal for example, for Gaussian distributions, and slightly more generally for Sub-Gaussian distributions. The sample mean is also a pretty good streaming algorithm, and it's somewhat robust to correlations between the samples as well. On the other hand, once we start dealing with distributions with tails that are heavier than the Gaussian, then the sample mean in general performs pretty badly. The next thing you might be wondering about is, what about all these tail bounds we learn, let's say in a first class in randomized algorithms? So let's try to apply some of these tail bounds and see what kind of sample complexity guarantees we get. So as mentioned before, the sample mean is optimal for Sub-Gaussian distributions, and the sample complexity we get is this expression here, where again, epsilon is the additive error, delta is the failure probability, and here sigma squared is the variance of the underlying distribution. But Sub-Gaussianity is a really strong assumption. So let's take a look at a different tail bound and see what we can get. And a good example, a good candidate is Bernstein's inequality, which makes a different assumption. It assumes that the distribution has support that is bounded within some constant width interval. And in this case, we get this new sample complexity expression, this bound. And the difference between this and the previous bound is this additive 1 over epsilon times log 1 over delta term. And the thing to note is that if the distribution has variance that is smaller than epsilon, then the second term actually dominates the first one. So there are some regimes where the second sample complexity bound is strictly worse than the first bound. And in general, if we try to apply different sorts of tail bounds, what we're going to get is that we require different sorts of assumptions, and then we're going to get sample complexity bounds that look slightly different. So what this is suggesting is that something smells fishy. Maybe the sample mean isn't quite the right thing, isn't quite the optimal thing to do. And indeed, we know that Chebyshev's inequality is tight. So in general, the sample complexity of the sample mean is pretty bad. It's inverse linear in the failure probability delta. This is in contrast with the logarithmic dependence we would typically expect from an exponential tail bound. So in general, sample mean does not enjoy any exponential tail bounds, so it performs really quite badly. At this point, it is prudent to ask, so what's actually achievable? What's the right sample complexity for this mean estimation problem? And to see that, we're going to look at the Gaussian special case, because Gaussians are limiting cases for many statistical problems. So we're given samples from some Gaussian with unknown mean and unknown variance, and we're trying to estimate its mean. As mentioned before, the sample mean is actually optimal for Gaussians. So that gives us a sample complexity upper bound, that is this expression, through pretty straightforward calculations. This part we've seen before on the previous slide, and the constant of 2 is the explicit constant that was hidden by the big O notation before. And as it turns out, for Gaussians, it's actually not very difficult to show that this sample complexity is essentially completely tight. In particular, the sample complexity upper and lower bounds are off by only a 1 plus little or 1 factor. So for the Gaussian case, we understand the sample complexity completely. Given this, it is natural to ask, then, is it possible to construct a mean estimator with this sample complexity, including the optimal constant of 2, and the mean estimator should work not only for Gaussians, but for all distributions with finite variance? And this is the problem we address in this paper. This is the right time to talk about the previous works along this line of work. Catoni, in his seminal paper that initiated the whole line of work, observed that if the distribution's variance is known very accurately, then it is possible to attain the sample complexity, including the optimal constant of 2. And Catoni, along with another paper by De Vroy et al., they also observed that even if the variance isn't known, but if we make the additional assumption that the distribution has finite and bounded fourth moment, then we can first estimate the variance very accurately, and then use Catoni's estimator to again achieve this optimal sample complexity that achieves the Gaussian sample complexity. And in this work, we are going to drop both of these assumptions, essentially. Last thing to note in terms of previous work is that if we didn't care about the optimal constant, if we only want a bigger optimal sample complexity, then we already know how to achieve this. And this is through the pretty standard result of the median means algorithm that's been known for several decades by now. Though the thing I want to note is that the explicit constant, at least the best analysis I've seen for the median means algorithm, it has a constant of 32 as opposed to the right constant of 2 that we're trying to achieve, and that's off by a factor of 16. The main result of this paper is that it is indeed possible to construct a mean estimator with the correct sample complexity, including with the correct constant of 2, across the entire set of distributions with finite variance, without making any of the strong assumptions made in previous work. And furthermore, our estimator is computable in linear time. Notice that as it is currently written, the theorem bounds the sample complexity n in terms of the error epsilon and the failure probability delta. And here, the sample complexity bound depends on the variance of the distribution, which is a priori unknown. So as it is currently written, the theorem statement isn't terribly useful. So the theorem we actually prove is a reparameterization of this theorem, where we fix the number of samples n, and we fix the failure probability delta, and we just ask, what is the best additive error we can get? And this additive error is going to naturally scale with the standard deviation of the distribution. Without further ado, this is our optimal mean estimator. Given our n samples and given the specified failure probability delta, the first thing we do is we compute the median means estimate, which we denote by kappa. Recall that median means is already a bigger optimal estimate. The next two steps are going to refine this initial estimate into something that is as good as mathematically possible. So in the third step, what we do is we solve for alpha in this equation. For now, the only thing you need to know is that this left-hand side as a function of alpha is piecewise linear and also increasing. And so there's some structure that is going to allow us to solve for alpha efficiently. Once we have alpha, all we do is we plug it into this right-hand side to compute our final estimate mu hat. Now that I've thrown at you these two rather complicated equations, let me try to explain exactly what the estimator is doing. It turns out there's actually a very simple combinatorial interpretation at the end of it. So again, recall that the estimator is compute median means estimate, solve for alpha in this first equation, plug it into the second equation to compute the final estimate mu hat. In order to simplify these two equations, the first observation is that this estimator is not too hard to check. It is shift and scale invariant, in the sense that if we apply the same linear transformation to all our samples, then the final estimate is also going to respect the same linear transformation. And what this means is that it suffices for us to only analyze distributions that have mean 0 and variance 1. The second simplifying assumption we can observation we can make is that if we look at the mean estimate as a function of the initial estimate kappa, so ignore for now the fact that we use the median means estimate, just treat mu hat as a function of kappa, it turns out that the final estimate is not very sensitive at all to what the initial estimate is. So combined with the fact that we will end up using the median means estimate as the initial estimate, which is very good to begin with, as a simplifying assumption, we might as well assume that kappa is equal to the true mean, which by the previous assumption is equal to 0. So what this lets us do is simplify these two equations into something that is a little bit more palatable like this. But even then, what do these two equations mean? So I'd like to draw attention to the second equation where we actually compute the mean estimate. Just for now, ignore the 1 minus min term, the multiplicative term. What we end up with is just the sample mean. So what this means for our estimator is that it truncates for each sample some fraction of the sample before computing the sample mean. Now the question is, how do we decide how much of each sample we are going to truncate? And that is governed by the first equation. What the first equation is saying is that we will throw out a total weight of 1/3 log 1 over delta many samples in the sense of sums of fractions. And in order to distribute these fractions we're throwing out, for each sample, we will truncate a fraction that is proportional to its square distance from the true mean. And this min with 1, all that's saying is that we never truncate more than the entirety of the sample. So this gives a very clean combinatorial truncation-based interpretation to what the estimator is doing. It's just truncating 1/3 log 1 over delta many samples in a way that it respects square distances of the samples from the true mean. And this is what the estimator is doing. Perhaps the most opaque and maybe a bit unmotivated part of our estimator is that we throw out exactly 1/3 log 1 over delta many samples before we return the sample mean. So on this slide, I want to give you some intuition as to why this magic number of 1/3 log 1 over delta, why that deserves to work through the basic example of estimating the mean of a Bernoulli coin. So consider taking n flips from some Bernoulli coin with bias p, and the interesting regime is when p is very close to 0. For the purposes of estimating the mean of a Bernoulli coin, all we care about from the n flips is the number of heads total. And that, of course, is distributed as a binomial distribution. But if we also take n to infinity, then that binomial converges to a Poisson distribution with a Poisson parameter lambda that is equal to n times p. So on the right here, I have plotted for this blue dash curve, the logarithm of the Poisson, where I've chosen lambda to be equal to 100 to be concrete. Further recall that the goal of this paper is to get mean estimation at convergence that is equal to the Gaussian performance. So I've also plotted this red solid curve that is the logarithm of the corresponding Gaussian with the same mean and variance 100 as the Poisson does. So as you can see, the issue with the Poisson distribution is that it has a heavier right tail than the Gaussian does. So what this means is that if the number of heads is distributed as a Poisson, then somewhat likely we're going to see too many heads. That corresponds to a heavier right tail. So naturally, what we want to do is we want to subtract off some number of heads before dividing by n to return as an estimate. Now the question is, how many heads do we subtract? To see that, we take the delta tail of the Gaussian distribution and also the delta tail of the Poisson distribution. And we look at this gap. This gap is exactly how many heads we should truncate before dividing by n and returning as an estimate. And this gap turns out to asymptotically be exactly 1/3 log 1 over delta. And this is exactly what our estimator does. It throws out 1/3 log 1 over delta many heads before dividing by n, before returning it as the final estimate. And this is guaranteed to achieve Gaussian performance in mean estimation. Given the time limit, I'll just make a few remarks on the analysis of our estimator. So recall that the main theorem is just a tail bound on the estimator, and therefore a canonical approach to proving the main theorem is to derive our own custom Chernoff bounds. And by Chernoff bounds, I mean an inequality of the form where the one-sided tail of a random variable is upper bounded by something proportional to its moment generating function. But if we follow this line of thought, then we quickly run into two very important issues. The first issue is that in order to handle the moment generating function, what we usually want is a sum of independent terms. But in this instance, what we have as our estimator is a sum. It is a sum, but it is of dependent terms because of this alpha parameter from the first equation. And in particular, this alpha parameter is introducing dependencies across all these summands. So our solution is, instead of proving a Chernoff bound directly on the estimator, we're going to find proxies of the estimator that are indeed sums of independent terms, and we're going to prove Chernoff bounds on those instead. The next issue is that we're trying to bound the moment generating function of these proxies across a really wide class of distributions, namely all distributions with mean 0 and variance 1. And it turns out that this bound is equivalent to an infinite dimensional optimization problem, which is too complicated to handle. And our solution to handling that is to drastically simplify it using minimax theorems and using a linear programming duality. The last note I want to make is that we believe that this analysis framework is generalizable to other statistical problems as well. And therefore, I really encourage you to either read the paper or watch longer versions of this talk on YouTube to learn more about the analysis. Let me wrap up with some brief notes on future work. On the statistical front, the obvious question to ask is, can we also do mean estimation with the right constant in high dimensions instead of just one dimension? I'm happy to report that in a new paper with Paul in ITCS, we made some partial progress in the regime where the dimensionality is extremely high. On the computational front, even though our estimator is already computable in linear time, we really only know how to do this in a traditional RAM kind of model. So for the purposes of practically deploying the estimator, it is important to ask, can we do this also in restricted computational models, for example, in streaming models and in distributed models? This is the end of the talk. Thank you for watching, and please feel free to contact me if you have any questions.